Let's now start with lecture 4, which is about process scheduling. Here you have the instructions about which parts you should read in the main textbook, plus, as always, the extra facultative readings. And when it comes to the objectives of this lecture, the idea is that we will go deeper into processes, threads, and their scheduling and execution, of course. We will look at different types of systems, namely batch system, interactive system, and real-time systems. And let me say right now that you can take entire dedicated courses about real-time systems. So I'm not going to go too much into details here. It's just an overview of them. And then we will also discuss challenges when it comes to scheduling in relation with multiprocessor, multi-core architectures. And let's start with the introduction. So we have discussed in the previous lecture about the fact that we have processes which can have a single thread or they can be multi-threaded. And we said that the operating system is performing a lot of context switches in which it basically changes the thread that is being executed from one to another thread. This can be different threads that belong to the same process. This, of course, implies that we are talking about kernel threads of a multi-threaded process, but they can also be threads that have nothing, well, so that they do not belong to the same process, right? They can be two threads from two different processes. One thread that is started could actually run parts of the operating system code and so on. So the first distinction we need to make when we talk about scheduling is about the type of processes we have. We have CPU bound and input-output I/O bound processes. And this is what is being shown in this figure, okay? So a CPU bound process is a process that once it gets access to the CPU, so it goes into the running state, it is most likely going to stay there for long periods of time because it needs the CPU to perform, to run its instructions. If you think about a data analysis process that is doing a lot of complicated operations over data, if you start to run that process, then most of the time will be spent by running instruction at the CPU, okay? And sometimes this process might request the input output, let's say, to read some data from a file or to store some data, but those are events that do not occur frequently. Most of the time is using the CPU to actually run the analysis. On the other hand, we have I/O-bound processes. These processes make heavy use of input-output requests, system calls, and so on. So what it means is that with good probability, when you start running such a process, when you decide to schedule such a process, it will not take a lot of time before the next instruction run by such process will actually request some kind of input or output. Don't let yourself be fooled by the name here. When we say I/O bound, it does not mean that it takes a lot of time to do input or output operations. It just means that the frequency with which these processes are requesting input or output is high. So if you schedule such a process, there are good chances that in a relatively short period of time, this process will actually, let's say, launch a system call because it needs input output. And that means that the process will be moved into the waiting state. Now, if we think about when the operating system can actually take scheduling decisions, then we have different possibilities here. Of course, when you create a process, since you use a system call, let's say fork, for example, that is a point in time in which the operating system has the power to take a decision. Should I keep running the parent process or should I run the child process? Similarly is when you terminate a process, that's a point in which you give control to the operating system, and one of the things the operating system can do is to decide what is the process I will run next. And then we have input-output requests and input-output interrupts. So all these four, let's say, possible moments at which the operating system can take decisions about what to schedule. We also have elapsed time. I'm going to discuss this in a second. They are about non-preemptive scheduling. So if the operating system can only use the first four options to take scheduling decisions, then we are talking about non-preemptive scheduling. It does not mean that processes cannot be interrupted when these are the criteria used to schedule processes, non-preemptive scheduling, but it means that if they get interrupted, it's because one of these four conditions or situation is happening. On the other end, we have an additional point in time to take scheduling decision, which could be elapsed time. So we could create a system in which every 10 milliseconds, we wake up the operating system and we let the operating system decide, should we keep running the process we are running now, or should we run a different process? If we include this option in our scheduling, then we are talking about preemptive scheduling, in the sense that the process can be preempted after a certain period of time, so the operating system can actively decide the condition upon which it will be preemptive and say, well, in 10 milliseconds, I will wake up again, so that I can take my next scheduling decision. Okay, this is with elapsed time. Otherwise, we talk about non-preemptive scheduling.